So we saw before when we looked at and or versus XOR that in the case of and or, we only needed 2 nodes, but in the case of XOR, we needed 3. The difference between 2 and 3 is not that big, but it actually does turn out to be big if you start thinking about having more than simply 2 attributes. So let's look at generalized versions of OR and generalized versions of XOR and see if we can see how the size of the decision tree grows differently. So in the case of an n version of OR, that is, we have n attributes as opposed to just 2, we might call that the any function. That is a function where if any of the variables are true, then the output is true. We can see that the decision tree for that has a very particular and kind of interesting form. Any ideas, Michael, about what that decision tree looks like?
So going off of the way you described OR in the 2 case, we can start with that. And you pick one of the variables, and if it's true, then yeah, any of them is true. So the leaf is true.
What happens if it's false?
Well, then we have to check what everything that's left. So then we move on to one of the other attributes, like A2.
Mm-hmm.
And again, if it's true, it's true. And if it's false, then we don't know.
We'll look at A3.
Good idea. This could take some time.
Yes. Oh, that's actually an interesting point. Let's say if there were only 3, we would be done, right?
Right.
But wait, what if there were 5?
Then we need one more node.
What if there were n?
Then we need n minus 4 more nodes.
Right. So what you end up with in this case is a nice little structure around the decision tree. And how many nodes do we need?
Looks like 1 for each attribute, so that would be n.
N nodes. That's exactly right. So we have a term for this sort of thing. The size of the decision tree is, in fact, linear. n. And that's for any. Now, what about an n version of XOR?
So XOR is if one is true but the other one's not true, then it's true, and if they're both true, it's not clear how to generalize that. So why not?
So, well, the usual general version of this we like to think of is parity. All parity is a way of counting. So there's usually 2 forms of parity that we worry about, either even parity or odd parity. So let's pick one. It doesn't matter. Let's say odd. I like that. We'll do odd parity. And all that works out to be in this case is if the number of attributes that are true is an odd number, then the output of the function is true. Otherwise, it's false. Got it?
Got it.
Okay, so how would we make that decision tree work?
Ooh. Well, we got to split on something, and they're all the same, so let's split on A1 again.
Okay. So what do we do if A1 is true versus being false?
We don't know much if A1 is true. We have to look at everybody else.
Right. So let's look at A2. What if A2 is true versus false?
Well, if A1 and A2 are true, then the output is going to be whatever the parity of all the remaining variables are. So we still have to do that.
Yep. And I'm already running out of room, so let's pretend there's only 3 variables. What's the output?
All right, so the far left, there's 3 trues, which is odd, so the output is true.
Yep.
The next leaf over, only 2 trues. A1 is true, A2 is true, but A3 is false. So that's 2 trues, which is even, so the answer is false.
Mm-hmm.
And is this pattern continuing? Now we've got, no, so then it's false again, because we've got 2 trues and a false to get to the next leaf.
Mm-hmm.
Then we've got 1 true to get to the next leaf, so that's true. Oh, that looks like XOR.
It looks just like XOR. In fact, each one of these subtrees is kind of a version of XOR, isn't it? Now what we have is we have to do the same thing on the right. So we got to redo A2, and we're going to be in the same situation before, and we're going to start drawing on top of each other because there's just not enough room. So what's the answer to the one on the very right, where all of them is false? All of them are false.
So that's an even number of trues. 0 is even, so that's false.
Okay. And so in the case where only A3 is true,
True.
it's true, and we just keep going on and on and on again. Now imagine what would happen. In fact, let me ask you, Michael, what would happen if we had 4 attributes instead of 3?
Then we'd be really tired of this game.
Yes, and I'm already tired of this game. So the question is,
we get a whole other level of this tree.
Yep, we have to, it just goes on and on and on, and nobody wants to think about it anymore. So how many nodes do you think there are?
Well, for 3, there was 1, 2, 3, 4, 5, 6, 7, which seems suspiciously like 1 less than a power of 2.
Mm-hmm. And that is exactly right. You need more or less 2 to the n nodes, or
2 to the n, maybe minus 1.
Yeah. But let's just say big O of 2 to the n. Everyone watching this is a computer scientist, so they know what big O means. Okay, so you need an exponential, therefore, as opposed to linear number of nodes.
Gad.
Yeah, so you very, very quickly run out of room here. You very, very quickly have a really, really big tree because it's growing exponentially. So XOR is an exponential problem and is also known as hard. Whereas OR, at least in terms of space that you need, is a relatively easy one because it's linear. We have another name for exponential, and that is evil. Evil, evil, evil. And it's evil because it's a very difficult problem. There is no clever way to pick the right attributes in order to give you an answer. You have to look at every single thing. And that's what makes this kind of problem difficult. So just as a general point, Michael, I want to make is that we hope that in our machine learning problems, we're looking at things that are more like any than we are looking at things that are more like parity. Because otherwise, we're going to need to ask a lot of questions in order to answer the parity questions, and we can't be particularly clever about how we do it.
Though if we were kind of clever and added another attribute, which is like the sum of all the other attribute values, that would make it not so bad again. So maybe it's just a kind of bad way of writing the problem down.
Well, you know, what they say about AI is that the hardest problem is coming up with a good representation. So what you just did is you came up with a better representation where you created some new variable, let's call it B, which is just the sum of all of the A's, where we pretend that, I don't know, true is 1 and false is 0. This is actually a really good idea. It's also called cheating because you got to solve the problem by picking the best representation in the first place. But you know what? It's a good point that in order for machine learning to work, you either need an easy problem or you need to find a clever way of cheating. So let's come back and think about that throughout all the rest of the lessons. What's the best way to cheat?